extended surface. We call it extended surface. So if you go to the textbook, okay. So if you go to the textbook, I think the subtopics under this one is called heat transfer from thin surface. Okay. So another word is a extended surface. Okay. So extended surface actually means a fins. Okay. So if you look to the textbook, where is the textbook? Yeah, this one. Okay. So when you go to the textbook, it's already mentioned here the chapter 3. Yeah, this one. Okay. So heat transfer from fin surface. Okay. So you not really find extended surface, but it is named as a heat transfer from fin surface. So fin surface or extended surface actually is the same thing. Okay. So what is the extended surface or fin? I think you might some of you might familiar, some of you probably not have seen before. Okay, but I think majority of you know that this kind of application in our routines, okay, in our daily life. Okay, so this kind of component, okay, or or assembly, okay, used to uh, release the heat, okay, control the other component that require control environment or control condition of temperature, for example. Okay, so this is example of fins, okay, or extended surface. Okay, so this kind of a component in the mechanical system is mainly due to the environment, the temperature of that particular system. Okay, so this is another example. Okay, fins. Okay, I think this is from the side. Okay, that develop or design fins. Okay, to apply in the various electronic system. Okay, also this one. Okay, you can see here there is a variety of fin design. Okay, okay, so regardless of any fin design or any extended surface design, okay, so this extended surface used to transfer from that particular component that we want to apply. Okay, so how this component can improve the heat transfer is actually by having the effect of convection. Okay, so this means combined effect of conduction and convection. Okay, so imagine that this is the fin. Okay, so this fin seems like you want to transfer heat from one side to other side. Okay, so this is an example of you want to from this side to other side, from lower side to the upper side. Okay, so between this you are I mean the fluid flow. Okay, so of course the heat will be transfer as well as convection. So here the heat will transfer to the conduction. So in here you will transfer by conduction plus heat by convection. So there is two effects. So that's why we call it is a combined effect of conduction and convection. Okay. So well, this is another type of fin. Okay. I mean, the most simple thing is if we want to extend the heat transfer from this particular surface. Okay, let's say this is the surface that you want to pull down. Okay, So you might introduce another surface, okay, with this main surface. This is the main system or object. This is, we call it a extended surface. Okay. So we know that one way to improve or to increase the heat transfer is by increasing the area. Not too much, because if you want to increase the area in the very high proportion, it may involve in the increase in the cost of the system in general. Okay, so by introducing extended surface, you may have a heat transfer by conduction here, Q conduction, okay, as well as you may have heat transfer by convection if it is exposed to the environment or the surrounding. Okay. Okay, so that is the application of electricity. So regardless of any kind of design of the fins, okay, and divided into a basic type of which is in the design. Okay. In the textbook, it's already mentioned here. So there is a uniform cross section. Okay, so this kind of fin shape. You have a non-uniform cross section. Okay, meaning that the cross section of the fin is changing as the x is increased. Okay, you may have annular cross section. Okay, at which the fin is applied to the system like a piping system. Okay, and you may have another type fin called a pin fin. Okay. Okay, so each design or each fins have their own calculation in order to calculate the corresponding heat transfer and also the temperature variation across the fin. Okay, so in general, in order to analyze the fins, okay, so we have to consider heat conduction analysis as well as heat convection analysis. So this kind of topic is actually introduction to the convection calculation, okay, before we go to the convection analysis in much more detail. Okay. Okay, let's say we want to start to analyze the fin. Okay. So we know that we need to consider the effect of conduction, the effect the conduction, then the effect of the convections. Okay. Okay, we look to the general fin equation. Okay, this is a method of deriving the equation that relevant to the fin application. So imagine that this is the fin that you want to introduce or you want to design in a particular surface. Okay, so at one particular elements, okay, at one specific elements, okay, so we want to know how much the heat move or the heat transfer from one side to other side, okay, due to the energy balance. Okay, using the energy balance, so you know that inputs. Okay, if you look to this particular equation, a particular a figure. So this figure, heat input, which is by conduction, okay, is equals to the heat rate by the conduction. Okay, so let's say this is the one, this is term one, okay, equals to the heat conduction on the other output side, okay, plus heat transfer due to the convection. Okay, at this one particular element. Actually, you may have another heat at the downside, but we just say that it is combined effect. Okay, so 1, 2, and 3. Okay, for one particular condition at which delta X is nearly 0. Okay, this means it's very, very thin. Okay, this slice. Okay, so we can see that the equation of this simplify into this form. Okay, which is the effect of due to the conduction and effects due to the convection. Okay, where T is the temperature distribution across the element in the x-axis. K is the thermal conductivity of that particular fin material. AC is a cross-sectional area of this particular element. Okay, so this is the AC. Okay, and P is the perimeter. P is the perimeter of the pin. Okay, might say that we can say that P is the pin perimeter. Okay, whether it is a square shape, whether it is a circular shape, whether it is probably triangular shape, depending on the fin design. Okay, as well as H. H is the convection coefficient is in the surrounding of the fin. So normally H is here. Okay, is the convection coefficient. Okay, of surrounding near in. Okay, so with the unit watt per meter squared Kelvin. T is temperature. What is a T infinity? T infinity is a T surrounding. Okay, so this is T surrounding. So this is the general equation that you might need to use in order to derive the equation, the final equation for the fin analysis. Okay, because we consider the effect of conduction and convection. So what we need to do from this equation, so we need to do some integration. Okay, it's same like a chapter 2. Okay, if you remember in the chapter 2, we have a general heat conduction equation, and then we need to find the boundary condition, and then we need to do some integration in order to find the temperature distribution and the heat transfer rate equation. Okay, so normally in the conduction analysis, okay, before we go to the simple analysis, the general equation, normally we have general equation, and then we need to have two boundary condition. Okay, two boundary condition, and two information. You need to find the first temperature distribution. Okay, and second, the heat transfer rate equation. Okay, so same fin analysis. So this is the general equation for the fin. Okay, same thing. Okay, the only difference is we try to simplify the form. Okay, originally we have this HPKAC. So it's actually when from here to here you are rearranging the equation. Okay, so that you can have this terminology. Okay, of temperature distribution due to the conduction and convection. And from here, from the first equation to the second equation, we change where the theta is the temperature distribution, temperature difference between the instantaneous temperature and the T surrounding temperature. And this term we transform into simplified form named as a M. Okay, so what is M? M is actually the some books call it is a fin parameter. Okay, but some book use as just a simple form that relate the properties of the surrounding related to the properties of the fin. Okay, in terms of thermal conductivity, the perimeter, and okay, some call it a fin parameter, but not always say as a fin. But this is just I want to give it familiar name so that you know that M is a fin parameter. Then you need to calculate, if you know the H value, the P parameter of the fin cross section, K is the thermal conductivity of that particular material of the fin, AC is the cross section. Okay, so we have this general equation and we need the boundary condition. Okay, so the boundary condition in fin case, we have four types. Okay, there is a four type of boundary condition. Okay, meaning whether we want to consider the fin tip. Okay, the fin has a tip which is very long, or the fin have a tip which the heat loss is negligible. Okay, this is a tip boundary condition for the fin. Or we can consider the fin tip has a specified temperature, or the fin tip has a convection effect. Okay, so of course you might say, you want to say which one is more common in case of the heat transfer analysis. Okay, in general, if you ask me personally, between boundary condition 1, 2, 3, and 4, the most common boundary condition for the fin tip is the last one, convection. Because we not design fin to be very long. We not say that the heat loss in fin tip is always negligible. Sometimes we need to consider, and sometimes we not sure what is the temperature of the fin. Okay, so for this reason, that's why I say that the boundary condition number 4 is almost commonly used in case of the fin tips. Okay, so imagine this is the fin. So this is the boundary condition at here. Okay, so this is the fin. So the fin, all these four boundary condition. So using the original equation of general fin equation, and using either of these one boundary conditions, so you need to produce the temperature distribution equation and heat transfer rate equation. Okay, let's say we go one by one. Okay, so firstly we go to the infinitely long fin. Okay, so using this equation, we try to solve actually from this term. Okay, you do the uh, two-stage integration, then you will got this general solution. Okay, so using this general solution and the boundary condition in the infinite long fin. So this is the boundary condition for the long fin. So you may get temperature distribution in this particular equation. So this is the equation of temperature distribution. Okay, if you rearrange this equation, you need actually T as a function of E negative mx, okay, times the TB minus T surrounding, sorry, a plus T surrounding. Okay, so this is your aim, because you want to know what is the temperature across the fin. Okay, that means the Tx from here, T when the x is to 0. This is T when the x equals to L. Okay, this is T. Then you want to know T is when the x goes to L over 2. Okay, so when you try to plot the temperature across the fin, so you may get this kind of pattern. Okay, so what is the TB? Is base temperature. TB is base temperature at fin base here, this one. Okay, at the body of the system before you introduce the fin. Okay, and the Tx is the temperature throughout the or across the fin. Okay, in the x direction. Okay, that is the temperature distribution. Okay, so this is equation first equation in the infinite long fin. The second one, when you do the using the heat conduction equation of the Fourier equation, so you might get the second equation for the long fin. Okay, so this is the first, this is second. Okay, so you can get the heat transfer for the long fin, okay, if you know the base temperature, the surrounding temperature, and all these fins parameter. Okay, fins properties. Okay, so like I say, every condition using general solution and the boundary condition, you combine this equation. Okay, actually I skip the process of derivation, because at the end you just temperature distributions equation and the heat transfer rate equation. Okay, so this is for the case number one, this one, infinite long fin. Second one is the negligible heat loss, okay, at fin tip. Okay, so using the same general solution and the boundary condition at the fin base and the fin tips, So you might get this equation. You may get this equation. Okay, so what is the equation for the temperature distribution? So this is a second condition of the fin tip. So you get Tx equals to cos. This is H is a hyperbolic cos hyperbolic function. Okay, this is supposed to be m L minus x. What is m? M is a you see that m equals to HP A divided by cross section AC. Okay, from where? From this one, from the general terms of the HP KAC. Okay, again this is cos hyperbolic function. Okay, divide by cos hyperbolic function for the ML. Okay, multiply by the difference in temperature between base temperature and the surrounding temperature plus the surrounding. Okay, so this is the temperature distributions for the case of negligible heat loss, and the second equation, which is heat transfer rate. Okay, now you have this a big longer equation. Okay, where like the infinite long fin, like you need to include the function. Okay, so heat transfer. Sorry, this is a negligible heat loss. Sorry for the typo. Okay, so heat transfer for negligible heat loss is equals to the square root HP KAC divided by the temperature difference between base and surrounding times the tangent hyperbolic, okay, of ML. What is M? M is the fin parameter, L is the length of the fin. Okay, so that is the second part of the condition. So the third part is when you know the temperature at the fin tip, specify temperature of fin tip. Okay, all these condition is happen at the fin tip. Okay, so again using the general solutions and the boundary condition, so you get this kind of temperature distribution. Okay, so again if you realize the temperature distribution from the first case to the third case now become a bit more complex. Okay, because why? Because like I say, we need to derive the equation so that it is considered as real condition of the fin application. Okay, so in the third condition or in the third case where we assume that the fin tip have their own temperature, so the temperature distribution will be in this kind of form. Okay, so again you have the hyperbolic function, okay, but in the more longer form of equation. Okay, so this is for the temperature distribution Tx, and another one is a heat transfer rate. Okay, again if you look here, in the case 2 we have tangent hyperbolic, but in this case you have longer equation of cos hyperbolic and sin hyperbolic function. Okay, so this is a third case, so you can imagine what happened in the fourth case. So this is a fourth case. Okay, number 4. Okay, convective at fin tip. Okay, so using general solution, and using this boundary condition at the base and the tip, so this is your temperature distribution. So you can see now is a longer equation, and as well as heat transfer rate. Okay, so that's why how to use this equation is depending on how you want to assume the condition at the fin tip. Okay, so if you want to use a simple equation, then you may say it is infinitely long fin, but in most cases, not all fin is considered a long fin. Then you may need to consider whether you neglect the heat loss at the fin, or you know the temperature, or you don't know nothing, and you assume the fin at the tip is normally has a convection analysis. So in most cases, like I say, the case number 4 is the most common one that we use. So in order to calculate the heat transfer rate for the case of number 4, so you need to use this equation. Okay. Okay, understand. So there is a 4. So okay, this is example of how the problems that related to the fins. Okay, of course, you need to choose the last condition where the convection from the fin tip. Okay. Okay, I want to show you this example. Actually, if you go to the textbook, I'm not sure whether this is the old textbook. The number is 3185. But if you go to the new textbook, probably it is 319 something. Okay, but anyhow, this example want to show you. So you have this condition of fin. You have circular fins. Okay, you have the properties of the fin with 10 millimeter diameter, length is 50 millimeter, and you have the fin is attached to a wall with a surface temperature of 350. So this means this is the diameter. This is a diameter of the fin. This is the okay 0.5 meter. Okay, are attached to a wall with a surface temperature of 350 degrees Celsius. So this means this is a base temperature, okay? Because it's the temperature at the surface of the wall. So this means here. So here is a 2 degrees Celsius. So the fin are made of materials. Okay, they not mention the material, but they give you the thermal conductivity of 240 watt per meter Kelvin. So that means the K value here is a 240. Okay. And then exposed to the ambient air or surrounding with 25 degrees Celsius. This means T surrounding here is at 25 degrees Celsius. Okay, and the convection heat transfer coefficient, the H value is a 250 watt per meter squared Kelvin. So first you need to determine the heat transfer rate, okay, which is Q dot, and plot the temperature variation of a single fin for the following boundary condition. So this means this is your case A or case 1, this is a case B, this is a case C, this is a case D. So this problem asks you to plot the temperature distributions, okay, as well as the heat transfer. The heat transfer is just the one single value, okay, but the temperature distribution is a function of X. So probably you need to divide the L into several points. For example, if this length is about how many? This is 50 millimeter. So probably you want to divide into interval of 10 millimeter. Okay, 10, 20, 30, 40, 50. So for each distance, so you plot the temperature distribution. Okay, I think I have this the answer for this. I think for heat transfer, you may get single value, Q for this, Q for this. For the second, this is for first, second. This is for the third. This is for the fourth. Okay, but for the temperature distribution, okay, like this, they are trying to plot. In fact, they plot at the different um, 5 millimeter distance. Eh? So if you look here, this is a 10 millimeter. Okay, and between this you have a 5 millimeter. Okay, so look here the temperature distribution. Okay, so this is the circle one, the circle gray. This is a long fin. Okay, second one, adiabatic fin tip, or this also meaning negligible heat loss. Okay? Because when the heat loss at the fin tip is negligible, so you say it is adiabatic. Okay, so this is negligible heat loss. Okay, condition number 2. Okay, number 3, fin with temperature of 250 degrees Celsius. So you have a specified temperature at the fin tip. Okay, with the triangle shape. This one, specified temperature. Okay, and the last one is a convection from fin tip. So this one, convection. So I guess, okay, if I put a number, this is case 1, this is case 2, this is case 3, this is a case 4. So you can see that what you can say from this variation or this answer. Okay, so you may have you may get heat transfer rate for each one, but the value will be different. Okay, but in terms of temperature distribution, you can see that the case 2, case 3, and case 4 is slightly similar, but case 1 is totally different from case 2, 3, and 4. So meaning that if you want to do the analysis, case 1 will give you answer, but in quite a big error compared to the 2, 3, and 4. Okay, so this is what we can summarize from this result. Okay, however, for the case 2, 3, and 4 is more reliable in terms of the final answer. Okay, since the temperature distribution across the fin is very close in each point. Okay, of course, for the case number 2, okay, you may neglect the heat loss if the area is very small, but if the area is significant large compared to the total area of the fin, you may need to cancel, or you may need to remove the case 2. You only have option with the case 3 or case 4. So again, case 3 only applicable if you know the temperature. And the good one, or the best one, if you have the case number 4 where it is a convection. Okay, so that's why, like I say, the case 4 is more common to use for fin analysis. Okay, even though why we have this kind of condition, because normally we need to put some, okay, normally this kind of boundary condition is required by the fin designer. Okay, so we want to know how much the fin can be designed in terms of the length. So that is the original approach that they want to do for the design the fin. Okay, next one, if they want to design the fin but they want to stick that we want to design the fin but the fin must be have temperature maximum at this value, then you may use this the third condition. Okay, or probably they want to design the fin but the fin have negligible heat loss because of the area at the fin tip is very small compared to the body of the fin, that you need to use the number 2 condition. And of course, if all these 1, 2, 3 is not applicable for the condition that you want to select, lastly, the number 4 is the only analysis that available for the heat transfer for the fin analysis. Okay. Any question? Any question before we go to the next part of the fin efficiency analysis? Okay, because the next part is once we already calculate the temperature across the fin and the heat transfer, we want to know whether how much efficient the fin installation in order to reduce the heat transfer or reduce the heat rate or reduce the heat loss or increase the heat loss, depending on what type of the heat transfer that you want, whether you want to increase or whether you want to decrease. Okay. Any question, guys? I will share again the attendance later in the last minute of the class. Okay, this topic is not include for your test one, but will be included in your final exam, if I'm not mistaken. Okay, because it's part of the conduction, but the conduction is in the later stage or in the later topics. Will be assessed during your final exam, but as part of the assignment I will include this as well as for the assignment. Okay, any question? So if not, okay, I'm owe you to give a second assignment related to the thermal resistance. Any question so far about the thermal resistance? I hope you can understand. Okay, let's we go to the textbook, whether you can see the example of fin calculation in the textbook, chapter 3. This is chapter 2. Okay. So the chapter of fin is started from page this one. Okay, page 179. So you may read this text about the heat transfer from fin. So you can see the description. So same thing that what I have explained here just now in the slide. Okay, how they simplify the equation. Okay, and now they want to solve using different case. Okay, so this is what I mentioned here, different boundary condition at the fin tip. Okay, so first infinite long fin, second negligible heat loss. You can see the final equation when they write in blue color. Okay, so this is for the fin tip, and this is for the heat transfer rate. Okay, so this equation is quite important if you want to consider case number 2. Same goes to case number 3. Okay, so this is the equation for the heat temperature distribution. This is the heat transfer rate for the case number 3, and this is for the case number 4. Okay, I'm not sure whether there is a table for this or not. If the table, then it is good if you can see how the equation evolve from the first case to the second case. I need to check from the summary. Sometimes the summary also have the equation. Okay, actually there is many information here, but not all cover in your test. Yeah, okay. So if you look, this is the summary in page 217. So you can see here, this is for the fin. Okay, so this is a temperature distribution for the different case. Okay, so this is case 1, this is case 2, this is case 3, this is case 4. So you can see how much the equation evolve from the simple equation only dealing with the exponential equation to the hyperbolic function, and to the more complex hyperbolic function. Okay, same goes to the, so this is for the Tx, this is for the temperature distribution across the fin, and this is for the heat transfer. This is for the heat transfer for the, this is Q dot, heat transfer rate. This is case 1. Okay, first without hyperbolic function. Okay, and this is the second, third, and fourth. Okay, so heat transfer now become longer. So that's why we not ask you to remember this. Okay, but we need you to understand how to use this. Okay, so you need to know at what condition you may need to use heat transfer for the tip condition, heat transfer specified temperature, or heat transfer in the convection analysis. Okay. Okay, guys. If there is no question, I will go back to the. Oh, just now, sorry. I want to share you some example in the textbook related to the fin. I'm not sure whether there is a specific fin example, because I think the example of the fin is very limited in this textbook. Okay, for that particular example of applying these four different condition. In fact, okay, this is the topics. This is the topics. The next one is, the next example is related to the, this is just a simple, no, this is not the fin equation, no. So in fact, there is no equation, no example that I just explained in the slide. Okay, so in this slide, for example, that I explained just now, okay, this is just to show you how to use the fin equation, okay, by considering different boundary condition. Okay, so if you look to the other exercise, other problem, they might say that solve the fin by considering the condition at the fin tip is long fin or adiabatic fin tip or negligible heat loss or convection. So depending, so you need to read carefully the problems, or you need to assume. Okay, so that's why in the analysis you need to specify your assumption before you proceed with the analysis. Okay, I will try to find some assignment or problem that use this kind of equation so that you can understand how to use the equation. Okay, is the why? Sorry, I will put it again in the